All right, so on the back of worksheet 2, I think we're in our packet on worksheet 2. This is discussing how you can use your calculator technology to find measure of angles and solve for triangles. And we're going to get, obviously, decimal answers, which is fine. Back in the day, they had to look these up on a chart, so that's not much better. But when they say things like solve the triangle, they want you to solve for everything that is not found. So like, for instance, on this triangle, the first thing I notice we don't have is leg A. So in a right triangle, if you know 2 of the legs and you want to find the third one, that doesn't involve trig. What does that involve? Pythagorean theorem. So you'd set up like a squared plus 20 squared equals 35 squared. And after doing a little Pythagorean theorem, you just subtract and square root, you get the square root of 825, which yes, it does reduce to a prettier number. But they went ahead and just wrote it as 28.7. Yeah, right there, man? Okay. Not okay. So because we're solving for the triangle, like that's a fine answer for this question. But then I want to keep going because there's 2 other things we don't know in this triangle. We don't know angle A and we don't know angle B. So again, it's your choice how you solve for the rest of the triangle. They decided to solve for angle A. I don't know why they didn't just call it A here. By setting up a cosine. So the reason they went with cosine, because that allowed them to use the leg of 20 and the hypotenuse of 35. Why was that smart of them to use cosine function as opposed to using sine? Say yes, it's much safer to use the values that were given to you in the problem if at all possible. If I used sine and I had to use the 28.7, and in the semi-likely event that I screwed up that problem, which I do, then I'm going to have 2 wrong answers instead of just 1. So it's safer to use the problems that are given to you originally. So that's why they went with cosine. And they didn't show this, but they set up the cosine of A equals 20 over 35. And then we talked about this yesterday. A is trapped inside of a cosine function. So how do you undo functions? You apply their inverses. So the inverse to a cosine function is called inverse cosine function. When you apply it to the left side, they just cancel each other. And when you apply it to the right side, this is the thing you're supposed to type in your calculator. So everybody practice this with me. First, check your mode. What mode do you have to be in? Degree mode. And then you're going to type the inverse cosine of the ratio 20 over 35. And y'all should get approximately that answer, 55.2-ish. And then they didn't use any trig to find the third unknown thing, guys. They said if this angle is 55.15 or whatever they rounded to, how could you find the third angle? They have to add up to 180. Triangles add up to 180, right? The angles are a supplementary relationship. So 180 minus 90 minus 50, whatever it was, 5.15, gave them approximately 35 degrees. I can't read that. So that wasn't a really exciting question. That was like straight out of geometry. Moving on in life. This concept, oh boy, angle of elevation versus angle of depression. They are the same thing, right? So this kind of goes through the idea of what it means to be an angle of elevation. It's measuring from your line of sight up towards an object. So unfortunately, we are stricken with really stupid problems in like our history of math class. Like, I don't know about you, but have you ever noticed these questions are like, Mary's flying a kite. How high up is her kite? Like, I don't know if I care. The other issue I have with that question is usually Mary is flying the kite on the ground. Like, she's laying on the ground, according to that. Like, that's not how we measure things, right? It would make more sense if Mary measured from her eye level when standing up, created a triangle, and then added up the distance from the ground to her eye level at the end of the problem. But we never do that, because that makes the problem more complicated. But isn't that like how life would really happen? So if you think about, and maybe you've seen this, on the side of the road, especially before they do some construction, on roads or bridges or buildings even. Ladies and gentlemen out there in the road wearing construction vests, and it looks like they're looking through a camera on a tripod. They're surveying, and they're essentially indirectly measuring, because it'd be really awkward to have to measure long distances over canyons and whatnot with a tape measure. So they're doing some indirect measurement. So they're doing the trig essentially. I have a feeling someone else or a computer does the actual math calculations, but they're doing the measurement with the angle of elevation and depression based on how they're tilting their lenses. So it's kind of cool. Yes?
The kind of cameras you use now,
Yeah.
3D scans the whole
Isn't that awesome? I think that's so awesome. Oh, tech, man. Back in the day. So maybe they did throw a tape measure all across the canyon back then. What do we know? All right. Big tape measure. So angle of elevation is from horizontal eye level looking up at something. Angle of depression would be, again, your eye level, but looking down at something. The issue with angle of depression is it's not usually within the triangle that you have drawn. It's usually outside of the triangle. So that's why Taylor pointed out they're actually the same thing. We'll talk about that in pictures later, but the angle of depression is typically an alternate interior angle to the angle of elevation. Real quickly, I just want to show you what I'm talking about. Everybody's favorite question. Somebody's at the top of a building. That's a building. And the angle of depression, when they look down at something, is actually this angle right here. So in geometry and in trig and in algebra 2, you had a lot of these questions where they really wanted you to look at this triangle. Well, y'all, is that triangle even... Is this angle in this triangle, I guess, is my question. Like, kind of. Because this angle right here, which is the angle of depression, is it's equivalent, congruent, to this angle right here, which is called the angle of elevation. So what's nice about the angle of elevation is it's actually within the triangle. So if that was the triangle you were referring to in your math, you just would go depression, elevation, same measure, put them in the right spot on the triangle. Now, one could argue there's other ways to get around that. You could create this to be your triangle, because there's a little twin triangle over here that matches the red triangle. You could also calculate this angle, because he would be the complement to the angle of depression, right? If this was 40, this would be 50. There's a lot of ways around this question. Here's the problem I always run into. Man, I draw really awful pictures. They're bad. And they're not to scale. So I just have to kind of work with what I got. Here comes an awful picture. We're on your notes again. We got the Leaning Tower of Pisa. It's leaning. It looks like that. It's 55.9 meters tall. So the length of this tower, is 55.9 meters. And it's leaning so that it's 55 meters above the ground. Now, this is kind of what's hard for kids to understand. The actual height from the ground, known as an altitude, would be if you're at the top of it and you just drop an object down. So measuring straight down to the ground, you do create a right triangle. And this measurement here is 55. They want to know the angle at which it is leaning, which they're not real specific about what they're referring to, so I'm going to assume that they're referring to the angle that it's making with the ground. So I'm going to call this the angle that they're looking for. And now I got to think about what that means for my trig problem. We have to decide whether we're looking at a sine, cosine, or tangent problem. This is opposite of your angle, and this is the hypotenuse. So which one is that, guys? That's the sine. Very good. So sine of our missing angle is opposite over hypotenuse. And this kind of goes over what we just did in our notes. You solve for the angle by using the inverse function. So on your calculator, you're going to be doing the inverse sine. Oh, can't write. This is the side you actually type in, though. Make sure you have the 55 over 55.9 in the sine function as a fraction. What do we get? Okay. What was it? 70. Oh, 79.7. Not at all what I wrote down. Okay. Thank you. Which might make sense. I don't know. Never been to Italy. I don't know. All right. Submarine. Yes, Dan. You have a thought about that?
Field trip.
Field trip? Want to do some fundraisers?
Just gotta go measure it and then
Come back. All right. Here's my next drawing. That's the ocean surface. Like that? It's good. All right, submarine. A submarine is 250 meters below the surface. So down here is your submarine. I'm not going to even try to draw a sub. It's going to look like a hot dog or something. All right, so then it's going to start its ascent up to the surface, but it's not going to like pop straight up because that's not how that works. Ears would explode, I think. So it has a slow incline. It's going to go up to the surface here, and the angle at which it's ascending is a 22 degree from vertical. So they were very specific this time. This is the vertical component, which means this angle right here is 22 degrees. They want to know how far will the submarine travel before it breaks the water's surface. So they need to know this length right here. So methinks we're looking at a cosine. We have adjacent and hypotenuse. So we're going to set up the cosine of 22 equals 250 over x. And then this time x is just within the equation itself. So you're going to cross multiply and solve for x. So I know some of you know exactly what to type in your calculator. If this was a test question, what I would ask of you is that you literally write down what you're typing in your calculator. So if there's a silly, like I typed something wrong problem, I can at least give you credit for knowing what to do. But right now, this is x times the cosine of 22 equals 250. So to solve for x, you would divide both sides by the cosine of 22 degrees. And y'all already checked your mode, so that's not the issue. The other thing I might want to point out to you is get in the habit of closing your cosine function, even though it wouldn't matter in this particular question. It's just a good habit. And I've never been on a submarine, but your answer should kind of make sense. Like a little bit of logic would be helpful. What would come out to? 269.6 meters. Sure. I don't know. I mean, if I did my work and my answer came out to something ridiculous, at least I'd know I'd typed something wrong. Or if it came out negative, that's my favorite. It comes out negative when you're in radian mode usually. And then kids write that answer down. Okay. Sure. All right, construct. Oh, everybody's favorite. The ladder leaning on the house. How many of these have you done? I know, and it's really, I mean, it's not that it's an unimportant question. Like, you should be careful how you lean your ladder on the house. Yeah, it's kind of a weird house. Yeah, it's neither here nor there. Right? It's cartoonish. I'm very happy that they drew me a picture, but what you need to make sure you're careful of, where is this 70.1 degree angle?
To the right.
It's this guy, yeah. It's this angle right here. So, right, it's right here.
What?
On the right of the triangle.
No, but you said like on the right, so I'm thinking like on the right side, like the outside of the triangle.
Oh, no, in the triangle, right corner, right remote corner. Shush, Daniel. I think it's a really easy question, guys. I think we give this to geometry kids. How high up the wall does it reach? Sine, cosine, or tangent? It's sine, yeah. Sine of 70.1 equals x over 30. So in this case, when you go to cross multiply it, this is just a one-stepper, 30 times the sine of 70.1. If you go in the other order, you're going to get the right answer. Just please be careful that you close the sine function before you type multiplies by 30. And then I think we've all seen ladders on houses, and we've all seen houses. So your answer here should make a little sense. 28.2 feet, I think?
Yes.
Okay. So then they want to know the horizontal distance. That'd be, I don't want to call that x. I already have an x. Hi. Let's call it y. So again, your choice how you find y. Technically, you could go old school and use Pythagorean theorem, but that brings up the issue that Piper brought up, where you're going to be using an answer that you just got that maybe you screwed up. So what would be a way to set something up that wouldn't include the 28.2 that I already solved for? We could do cosine, yeah. So the cosine of 70.2, or 1, excuse me, equals y over 30. And this is another cross multiplier. So turns out that the horizontal distance is 10.2. Which, again, I've seen ladders, I've seen houses. I don't really know if that's an accurate measurement, though. 10.2. That's pretty far away.
I don't think that we're typically dealing with that big of an angle.
That's a big angle.
I think that's on the smaller side.
I think
typically I would keep my ladder closer to my house.
Yeah. I feel like that angle is not, that's not a good angle. This is a bad idea. Thank goodness we calculated it first.
It anchored into the ground.
Maybe someone's holding the ladder. They're all going to get wiped out by this poor ladder. Okay, so this is more, I guess, our speed of like, it's okay, at least it's not about a ladder anymore. So this is what indirect measurement looks like. So if we just want to use right triangle trigonometry, what you're doing here is you're kind of using surveying techniques, but again, you're laying on the ground when you're doing it, which I think is a little stupid, but whatever. They're measuring from his feet. Cool, cool. And they're going to do indirect measurement with two different right triangles. So the first right triangle that we're going to look at is this guy right here, this blue one. Oops. And then the other right triangle that they're referring to is this gigantic one. Oh my gosh. But here's the problem. Neither one of those triangles will actually calculate the height of the tower. The tower is from here to here. So if I call this blue height right here an X, and I call the red height from here to here a Y, oops, no, whatever you're doing, stop. Okay, how can I find the green height?
Y minus X.
Very good, Y minus X. So all it's going to take from us is a couple of right triangle trig problems. So the blue triangle, which I've made such a mess, I might want to just rewrite it over here. Well, that doesn't look like a good triangle. Oh well. The angle of elevation from the ground up would be 30 degrees. And then we're trying to find X, and I know that this distance is 100. The only difference in the red triangle would be that the angle of elevation is much bigger because we're looking higher. And I called it Y. All right, find X, find Y, subtract them. Here we go. Fun times. We're going to solve the same trig proportion. They're both going to be tangents. So we have the tangent of 58 equals Y over 100. And then we have the tangent of 30 equals X over 100. Now I know some of you are looking at this going, I feel like there was a simpler way. There is! And it's diving into the law of sines and cosines, which we'll get to that later in the chapter, right? Y comes out to, let's see, 160, I believe. And then X came out to 57.7. So when you find the difference between them, I think we get 102.3 feet. So that's a good example of using right triangle trig to indirectly measure something that we just can't measure. Unless we want to use something else, which we will learn about in a couple, well, probably next week. No, I take that back. It won't be next week. All right, so now you can officially finish that homework assignment from yesterday. You're looking at worksheet 3 and 4. Remember that your book work is on the back of worksheet 4. Hoffbauer was super sweet and copy the book work and circle the problems you have to do. Can't get any better than that, guys, okay? So we're doing homework. We're doing it. We're doing our homework. Can you find worksheet 5, please? 5 has a lot of vocab on it, so I'm going to apologize in advance for... I'm going to hop around a little bit in the slides. Worksheet 5 is going to talk to us about arc length, angular velocity, and linear velocity, which I already heard from Trig Kids last hour that they were not happy to hear that that's back. But it'll be better, okay? Second time around, you're going to love it. I think. Maybe. All right, so first, a little bit of vocab. This is not on your notes yet, so don't panic. Just a refresher from maybe your previous experience in trig and algebra 2. When we're measuring angles, you measure from an initial side, which when we look at it on the coordinate plane, or eventually the unit circle, is the positive x-axis. And then your angles measure in a counterclockwise notation, and that's how they indicate positive measurement. So give me an estimation for how big you think this angle is from here to here. Pretty good estimation. She went 120. I like it. 119. Very specific. You're all the ballpark, and I'm not even going to attempt to guess. So there you go. To bring back another vocab term, though, can you find me a coterminal to that angle? So if we think it's 120, I'm going to go with Taylor's because she was the first brave soul. What would be another angle?
Then you could have 60 on the other side. Oh,
that's the reference angle. If I measure 90, I'd be right here. So yesterday we learned that coterminal meant you add or you subtract rotations. Negative 240 would work. That would land you in the same spot, wouldn't it? Okay. You could rotate once through and come back. 480. That would work. Okay. So I just kind of brought back another vocab word because that's coming up in the slides too. So I don't want to confuse my readers of my slides later. I'm just going to ignore all this. Moving on. All right, so this is on your notes. At the beginning of your notes, it talks about degrees, minutes, and seconds. So when we measure an angle, we know we can measure them in degrees, and you guys have a visual for what a degree looks like. And then if I tell you that you can take that unit of measure and subdivide it into minutes and seconds, that should remind you of something in your life. What else is divided into minutes and seconds? A clock. And if you look at our old analog clocks, they look very triggy, don't they? Yes, I mean, they're circles. They have things that rotate. Would it be a far-fetched idea to say that we could apply our unit of measure of angles to a clock? Maybe a clock is designed in such a way.
Is it?
Yes. Hey, Bob, what do you think a clock should look like? Triangle. Should we rotate it? No.
Wait.
There's no cyclical things during your day.
But,
Oh, now he's a deep thinker now.
yeah.
Oh, man. Just
Because a degree is equal to 60 minutes, right?
a degree is 60 minutes. Yes.
So you only have 1 degree of rotation over the whole clock?
No.
Okay.
Now it gets weird, doesn't it? Because now we gotta
So
start.
don't tell me it's based off of
Well, but it is, right? Kind of is. All right. So it's a little deceptive, yes. All right. So let's talk about this. So Daniel kind of spilled the beans there. He said there's 60 minutes in 1 degree, which kind of feels like a clock, but not. So I'm with you. How many seconds are in a minute? So how many seconds are in a degree? 3,600. Very good. So there's 60 minutes in a degree. There's 3,600 seconds in a degree. So what that means for us is we can take a portion, like here we have 56 plus some change of a degree, and we can change this little decimal part to minutes and seconds. So the first thing I want you to notice is the symbol notation. Obviously you know what a degree symbol is. When they use minutes, they use this little apostrophe looking thing. It's a minute symbol for math. And when they convert something to seconds, they use what looks like a quotation mark, and that's that's seconds. Okay? So this is the old way of doing it. This is how, like, the dinosaurs, this is how we had to figure it out. You guys have a much better way. Your calculator has a degrees, minutes, and seconds converter on it. So what I want you to do is in your home screen, type 56.735. And then when your cursor is right after it, don't hit enter yet, just have your cursor right here. Go to angle, which is second apps. And you have something that looks like arrow DMS.
Yes, number 4.
Do that. And it should pop out this answer. So that's nice. We're going to use that. That's much faster than the way we used to have to do it. Okay? What I used to have to do is take the decimal part and start multiplying it by 60 to figure out how many minutes, and then take the rest of the decimal, multiply that by another 60 to figure out how many seconds. Very irritating. I'm glad you guys don't have to do it.
What if there's a remainder?
You have to round, because we don't indicate anything else smaller than a second. No microseconds. I mean, maybe. I don't know. Maybe in, like, really important math. This isn't it. In fact, I can't even tell you the last time I worked with degrees, minutes, and seconds ever, besides teaching this
What is
class.
it supposed to be?
I think when you, in many facets of engineering, they will use it. Of course. Because in certain facets of engineering, it's going to make a big difference if your rotation is a second off. You know, like shooting things into space. Aeronautical engineer, you might need to, encounter this in the future. That little angle, just slightly off, and you might miss.
I guess when you're dealing with huge distances.
Yeah, and velocities, yeah. Okay, so now let's talk about what happens if we have degrees, minutes, seconds. I don't like it, and I'd like to convert it to a decimal equivalent. So in this case, there's 2 ways. You can either just literally type it in your calculator using the symbols. So what I want you to do is type 32, and then you can find the degree symbol back in that angle menu. So go back to that second apps menu and pull up degree. And then keep typing. Type 5 and pull up the minutes. And then this is why I don't like this method. Then you type 28, and you'll notice there's no seconds key in the menu, which really bothers me because there's like nothing in that menu. Why couldn't they just put seconds in that menu? So who remembers where seconds, the symbol for seconds is hiding? Yeah, the seconds is alpha plus. So use your green key. And then you can type the second symbol, and then it'll pop out this guy. But I'm going to show you how I would have done that question, because I really am irritated by having to go to the various menus and places. It bothers me. So I go old school, and I say 32 plus 5 divided by, if I wanted to convert that to a degree, how many minutes are in a degree? 60. And then I take the seconds, which is 28, and I divide that by, how many seconds are in a degree? 3,600. This is what I'd type on my calculator, and it would come out to the same answer. I just find that to be a lot quicker and easier, because I hate going to find those stupid symbols. But it's up to you. You will be asked to do this on your homework and subsequently on your test next week. So choose a method, practice it that way, and then you'll be fine. Yeah. Yes, it's all trig review. We have one lesson coming up on Thursday that's more trig review, and then that's the end of our concepts for the next test. We do have a unit circle quiz coming up on Friday, guys, okay? Which we haven't talked about it yet. We're going to develop it for the first time tomorrow. And then you guys are going to study. All right, so now I need to go around a little bit. This is on your notes, right? We talked about coterminal a few minutes ago, and we talked about how to find positive and negative coterminal. So remember, if you're in, where are we at here? If you're in degrees, you take your angle and you either add or subtract rotations in degrees. So that's why it's got a 360 there. If you're in radians, you either add or subtract a rotation in radians, which is 2 pi n. Remember, n is any integer, so technically you guys don't need to put plus or minus. You can just put a big plus sign here, because integers indicate they can be negative. So sorry about that. Oh, geez, that got ugly. Okay, so you don't have to put plus or minus. If you do, I'm not going to count you wrong, because I do it too. So look at the examples that are in your notes. This is what we did yesterday already, and you already did for your homework, so I don't even know why I'm doing these. It says identify all angles that are coterminal. This is the easy question. You don't actually have to find anything. You just have to set it up. So all angles that are coterminal means you're going to add, how do I call a rotation for radians? 2 pi, and then throw an integer, k or n or whatever you want to use. Yep. And then what about when it's 135 degrees? 360 k or n or whatever you want to use. So for all, I love that question because it's less work. If I asked for one positive and one negative coterminal, then you got to go do the actual calculations. It's a little annoying. All right. So now, could y'all flip to the next side of your notes? This is the stuff that my trig friends were just going, when I mentioned it. Okay, so S equals R theta. That is a formula you will be given on your formula sheet. It represents arc length. So if you have something that rotates from a central point, that means you can measure a radius, because that would be the distance from the center point out, and then you can measure the angle. So the arc length, so like a portion of the traveling here, a portion of the circumference, the formula we're going to be using is r times theta. But big note, you might want to highlight this. You have to measure theta in radians. All of the formulas we use for PreCalc are assuming that you're measuring your angle in radians. We like that in upper level math. Even though radians aren't really awesome for like real world calculations, it makes your formulas nice. Radians are awesome. Degrees are not awesome. So there's going to be a little converting, but it's okay. It allows us to have easy to use formulas. Do some highlighting. That's a formula you're going to use quite a bit. There's two other things we're going to be learning. The first one is called linear speed or linear velocity. The symbol they use for linear speed and linear velocity, it looks like a V, but it's got like a weird, like a van symbol. That's what it reminds me of. And then angular speed, they use this weird swirly W, which is an undercase, lowercase omega symbol. So linear speed would be how fast an object is moving on the perimeter of a a circle essentially. So like the thing I equate it to is if you had a piece of gum stuck to a wheel, like how fast is that piece of gum moving? Fast is the answer. I used to say bug, but then people got really eked out by that. I don't know why. Do you care that you roll over a bug? Because you do. Okay, so then angular speed would be how fast the angle is moving. They have, they change each other, right? If you speed up your angular velocity, your linear speed is going to speed up as well. So here's where the formulas come in. And I think what bothers kids when they first are introduced to these in Algebra 2 Honors or in Trig is that it just seems like there's 1,000 formulas and they just never know when to use what formula. So I think what's irritating about that is that there actually aren't 1,000 formulas. There's like 2 formulas, but you can change things and swap them out. So let me kind of show you what it looks like to swap some things out. So here we have our linear speed, which remember they're using, it looks like a V, but it's really this symbol. And it says you can find linear speed by taking your distance and dividing it by your time. So S is distance, right? That's the arc length we just found out. Well, as a mathematician, you're allowed to swap things out. So like for instance, on the last slide, you guys found out that S was R times theta. So what if I swap that out for R times theta? So now my formula looks like that. Well, there's another clue later on here that says your angular speed is found by taking your angle of rotation, which is theta, measured in radians, and dividing it by time. Well, look right here, guys. Who's that? It's angular velocity. So could I just come back through and say this is really R times W? Or omega, I should say. So what that tells me is that linear speed could be found by radius length times angular velocity. Could you please highlight that formula? That formula you're going to use almost in every single problem we do here. Now the trick comes in with the angular velocity. Angular velocity has to be in radians per time. But very few times in your math problems do they say something is rotating in radians per time, because it's hard to measure radians. So you might want to mark a little note here. You may need to convert RPM. What does RPM mean to you? Rotations per minute, sometimes revolutions per minute. That's a very real life thing. We often hear about, oh, it's got so many RPMs. So they might give you that as a clue, and you have to convert it to radians per minute. That won't be that hard though, guys, because one rotation is 2 pi radians. All right, we're about to get very chemistry-y. We've got some dimensional analysis coming up. Okay, lots of conversion and lots of watching labels. Make a big note to yourself though, because labels are really important here, right? So when you have linear velocity, you take distance and you divide it by time. Now what the distance and time are is totally up to you or the problem. And sometimes I'll be a jerk and I'll make it convert. So like the clue will be given to you in seconds and I want minutes. So you got to do a little conversion in the middle. Angular velocity needs to be in radians per time. The only problem is, like we just said on the previous screen, I don't know why I'm going to blue here. It may be, there may be a clue with RPM. So they might not just explicitly say, here's your angular velocity. You got to kind of do a little finagling there. Let's see what this looks like. Now this question's already done for you, so you don't have to write anything down, just watch. The first clue they give me, well, they want me to find angular speed, which I forgot what colors I was using, this one. And they also want me to find linear speed. So 2 things I need to find. And the first clue they give me is that you have 8.2 revolutions completed in 3 seconds. This is an RPM, kind of. So I'm going to start with that, and I'm going to use it to help me find angular velocity. So step 1, finding angular velocity. Well, I'm going to start with what they gave me, just like we do in chemistry class. 8.2 revolutions per 3 seconds. And angular velocity has to be radians per time. And I I'm reading ahead, making sure I don't have to mess with the time units. We don't, so I'm just going to leave the seconds as seconds. But I need y'all to help me convert revolutions to radians. What did you tell me about the conversion factor for revolutions to radians? 2 pi radians is 1 revolution. So 1 revolution I will throw in the denominator because I want revolutions to cancel. It is equivalent to 2 pi radians. And I'm a big believer, even in chemistry and physics classes, that I do this, because now I feel like I am most definitely on the right track. So I throw this into my calculator, 8.2 times 2 pi, I divide it by 3, and I already did this, let me just steal my answer. I got 17.2 radians per second. This right here, this is my angular velocity. That was one of the things they asked me for. So the second thing they asked me for is a linear velocity. And this is where trig kids were like, oh, what now? We have a lot of formulas for linear velocity from that chart, but the one I had you highlight, that's the important one. Linear velocity is most often found by taking your radius and multiplying it by your angular velocity. Y'all, you have both of those clues. Keep reading in the problem. Didn't it tell you that your radius, the point of from center to the edge, was 7? And you just found your angular velocity. So on my calculator, I can't do that in my head, it's 120.2. Now, the only thing I haven't done a very good job at is watching my labels. This was measured in centimeters, and remember, this was radians per second. And this is also confusing to kids because they're like, what happens to the radians? The radian measure is a part of the formula. So when you come up with linear velocity, the radian label is not there anymore. It cancels out within the work. So you ended up with centimeters per second. There you go. That's your answer. And that's pretty much every single problem I give you for almost all your homework problems and all your test problems are that. There's a clue about angular velocity. Figure it out. Use angular velocity to find linear velocity. Done. All right. So now that I've said this is pretty much how all your problems are, I'm going to do totally the opposite of that, and I'm going to give you a different problem. This is what you're going to see possibly on a couple homework questions, but just remember that that formula you highlighted, that linear velocity equals r times omega, that is probably the key to every problem. Go back to that formula and it's going to help you. So like for here, for instance, they want revolutions per minute. I'm giving you angular velocity. So go ahead and start with the angular velocity. And for some reason, they want me to go back and convert this to revolutions per minute. Wah. You have to convert two things. I need to convert radians to revolutions, and I need to convert seconds to minutes, which we can totally do. All right, let's start with revolutions. Radians to revolutions. What's the conversion? 2 pi. Who? Who to who? 2 pi radians. So that's going to go in the denominator, is 1 revolution. And then for time, I know you got this, guys. Seconds. How many seconds in a minute? 60 seconds in 1 minute. So I want 60 seconds up top here. And then I always come through, even now to this day, I will come through and watch my labels and make sure everything's canceling how I needed them to cancel. I'm going to end up with revolutions per minute, which is exactly what I needed. I'm on the right track. Could everyone please practice typing this in their calculator? When you do 2.7 times 60, it's okay that you don't use parentheses, but when you divide it by 2 pi, here you have to use parentheses because you're dividing by 2 times pi, and if you don't use parentheses, it's going to multiply by pi up top instead, so careful. And I got 25.8 RPM. Ish. If you don't get that, let me know. Okay. So I'm going to skip 6 for the sake of time, but we're going to keep on going here. Let's look at number 7. So they want me to find the radius. This is an unusual question, but I could see something in real life like maybe wanting me to find radius. Here's the problem though. This is a backwards question. They gave you a few clues, right? They gave you linear velocity, which if I think about my formula, That's r times omega. Hey, look who showed up in that formula. R. Could you please solve for r in that formula? You would divide omega over. So it would be your linear velocity divided by your angular velocity. Ladies and gentlemen, there's your linear velocity. What's this? Is it? It's a clue. It's a clue about your angular velocity. Okay.
Oh.
So 120 revolutions per minute. Not quite. Yeah, we got to do a little converting because it's not quite angular velocity. But Daniel says 2 pi radians in 1 revolution. And now we have angular velocity. Oh, but wait. They almost tricked me. Look at your time measurement. This one's measuring in seconds. This is measuring in minutes. One of these has to convert. Since we're already doing some converting, can we just go ahead and finish this one with the converting? So 1 minute is 60 seconds. What that's going to allow me to do is have an answer that is in angular velocity is going to be in radians per second. And then when I divide meters per second by radians per second, you're going to have the right units. All right, on your calculator, woo, 120 times 2 pi divided by 60 is like 4 pi, which is 12 point something. What is it? Okay. So 12.6 radians per second. Remember, guys, this is angular velocity. I think we're ready to go. We've got a linear velocity of 24.8 meters per second divided by an angular velocity of roughly 12.6 radians per second. And when I crank that in the calculator, I get roughly 1.97-ish. I don't know exactly what it comes out to. Depends on where you truncated your decimal to. What'd you get, Piper? Like roughly does the 6 round up at all? Okay, so 9.7 work. And then this is the measurement of your radius, guys. So think about your labels you were working with. What would be appropriate label for this? If you're not sure, go back to your problem. We had meters per second divided by radians per second. The radians cancel out within the formula. The seconds will cancel out, and you get meters. Very good. So I wrote really stupid. 1.97 meters. Woo, that was fun. Okay, so, real quick, I can get through this guy. We have a transportation problem where there's the road, and they want to figure out how much longer the outside edge is versus the closer lane. And it's written a little sketchy here, but you guys drive cars, so you could probably figure this out. This entire distance is not 14. It's each lane is 14. It's written a little weird here. So this entire distance from here to here is 28, right? So that's why they have this smaller arch as 1,000 for the radius and the larger one as 1,028, okay? They want me to compare the difference in arc length. So, oops, arc length, remember, is this formula, where theta has to be measured in radians. So y'all, I know this is 180 degrees, but that's not radians. So you'd have to do a little conversion or just think about it. It's pi, yes. So the smaller arc would be 1,000 times pi, and the larger arc would be 1,028 times pi, and the difference between them would be 28 pi, which humans don't talk like that. Can you crank that in the calculator? Is it about 88 feet? I think it comes out to about 88 feet. So that question really wasn't hard math. It was just kind of interpreting what they wanted, right? So what you guys are going to do for me now, on the back of worksheet 6, you'll see some bookwork. That's the bookwork for 238. That's the assignment for tonight. We're going to do more arc length practice problems tomorrow because I know you guys are like not feeling real good about them yet. but I'd like you to try to start up. Just remember that the linear velocity is r times omega. That's kind of the formula you have to keep using in all of the questions. It's your job to possibly take a clue about angular velocity and convert it to angular velocity.